I'm Sunshine Manabat from BSCE 3G, and this video is for MECH 312, Dynamics of Rigid Bodies. And this video is about the rotational motion, example number 1. Rotational motion, example number 1. A wheel is rotating freely at 1,800 revolutions per minute clockwise. It is subjected to a variable counterclockwise torque which is applied at time t is equals to 0. The torque produces a counterclockwise angular acceleration alpha 40 rad per second squared, where t is the time in seconds, during which the torque is applied. Calculate letter A, the time required for the wheel to reduce its clockwise angular speed to 900 revolutions per minute. B, the time required for the wheel to reverse its direction of rotation. C, the total number of revolutions, clockwise plus counterclockwise, turned by the wheel during the first 14 seconds of torque application. So, first we will going to compute the time required for the wheel to reduce its clockwise angular speed to 900 revolutions per minute. So we will take the counterclockwise direction as positive. So the angular acceleration is known as a function of time. We can integrate it to solve for the angular velocity. So the angular velocity given is in revolution per minute. So we need to convert it to rad per seconds. So letter A. Negative 1,800 revolution per minute. Negative because it is in clockwise direction, and as I've said earlier that we will take the counterclockwise direction as positive, multiplied by 1 minute over 60 seconds. 2 pi rad is equals to 1 revolution. So, negative over 60 seconds multiplied by 2 pi rad. So calculating this, we will get negative 1,800 over 60 multiplied by 2 pi rad. We now have negative 60 pi rad per second. So now that the angular velocity is in rad per seconds, we now can integrate. So using the formula, alpha is equals to derivatives of omega over derivatives of time. Cross multiplication, we have derivatives of omega is equals to alpha multiplied by derivatives of time. So we have given alpha, which is this 40. So it's to 40 dt. Integrating both sides, integral of derivatives of omega from negative 60 pi to omega is equals to integral of 40 dt from 0 to t. So we have omega from negative 60 pi to omega is equals to 4t squared over 2 from 0 to t. So we have omega minus negative 60 pi is equals to 2t squared minus 0. Canceling. So now, we have the angular velocity is equals to, transpose here, negative 60 pi plus 2t squared. So, and with this equation, we will going to substitute the clockwise angular speed, which is 900 RPM. And we will going to convert the 900 RPM to rad per seconds. Over 60 seconds, 2 pi rad, 1 revolution. So we have 900 over 60 multiplied by 2 pi rad. This is also negative because it is in clockwise direction. Negative 30 pi rad per seconds. So we will now substitute this negative 30 pi rad per seconds in our equation. Omega is equals to negative 60 pi plus 2t squared. So negative 30 pi is equals to negative 60 pi plus 2t squared. Negative 30 pi plus 60 pi is equals to 2t squared. 30 pi is equals to 2t squared. Divide both sides by 2. So we now have t squared is equals to 15 pi. Squaring both sides, we now have t is equals to square root of 15 pi, 6.86 seconds. So 6.86 seconds is the time required for the wheel to reduce its clockwise angular speed to 900 revolution per minute. So this is our answer in letter A. Letter B. The time required for the wheel to reverse its direction of rotation. The wheel changes its direction when its angular velocity is momentarily zero. Using the same equation, omega is equals to negative 60 pi plus 2t squared. So we will replace our angular velocity with 0 is equals to negative 60 pi plus 2t squared. So lilipat natin to dito, magiging 60 pi is equals to 2t squared. Dividing both sides by 2, we have t squared is equals to 30 pi. Squaring both sides, t is equals to square root of 30 pi. We have 9.71 seconds. So 9.71 seconds is the time required for the wheel to reverse its direction of rotation. So let's have letter C. Total number of revolutions clockwise plus counterclockwise turned by the wheel during the first 14 seconds of torque application. In total number of revolutions which the wheel turn during the 14 seconds is the number of clockwise turn during the first 9.71 seconds plus number of during the remainder of the interval. So n total is equals to n1 plus n2. First interval, we will going to integrate the expression for omega in terms of time will give us the angular displacement in radians. We will use the equation omega is equals to derivatives of theta over derivatives of time. Cross multiplication, we will have derivatives of theta is equals to omega multiplied by dt, wherein our omega is equals to negative 65 plus 2t squared. Negative 65 plus 2t squared multiplied by derivatives of time. Integrating both sides, integral of theta from 0 to theta 1 is equals to integral of negative 60 plus 2t squared multiplied by dt from 0 to 9.71. So we have theta from 0 to theta 1 is equals to negative 60 pi t plus 2/3 t raised to 3 from 0 to 9.71. Adding in our limits, we will have theta 1 is equals to negative 60 pi multiplied by 9.71 plus 2/3 multiplied by 9.71 raised to 3 minus 0. So we now have theta 1 is equals to negative 60 pi times 9.71 plus 2/3 multiplied by 9.71 cube. Theta 1 is equals to negative 1,220 rad. So we need to convert the rad to revolution. N1 is equals to 1,220 over 2 pi. So we have N1 is equals to 1,220 over 2 pi. 194.2 revolution clockwise. So for the second interval, we will going to use the same formula, the same equation. So derivatives of theta is equals to negative 60 pi plus 2t squared derivatives of time. So integrating both sides, integral of derivatives of theta from 0 to theta 2. Integral of negative 60 pi plus 2t squared dt from 9.71 to 14. So we have theta from limit 0 to theta 2 is equals to negative 60 pi t plus 2/3 t cube from limit 9.71 to 14. So we have theta is equals to negative 60 pi times 14 plus 2/3 times 14 cube minus negative 60 pi times 9.71 plus 2/3 times 9.71 cube. Calculating this, we have theta 2 is equals to 410 rad. Converting rad to revolution, M2 is equals to 410 divided by 2 pi. We have 65.3. Now that we have the N1 and N2, or the clockwise and counterclockwise revolutions, we can now solve for the N total, or the total number of revolutions. N1 plus N2. 194.2 plus 65.3. N total is 194.2 plus 65.3. We have 259 revolution. So 259 revolution is the total number of revolutions, clockwise plus counterclockwise. So this now concludes our example number 1 in rotational motion.